Everyone. Also, another quick announcement. So today we have more nurse tours, and so for people taking today's nurse tour, so if you have signed up on that Google spreadsheet, the tours will leave here at 12:40, and then they'll take you to the nurse building, and then you'll be following Paul for that, who's sitting right there. There are also more spots available for the nurse tours if you haven't taken one yet. They're on the Slack channel. There's a pin with a spreadsheet where you can sign up if you want to see the supercomputer here. But other than that, so for a second talk today, we'll learn about large language models from Sewon Min, who is a professor here at UC Berkeley in EECS, and also a researcher in the Allen Institute. So please join me in welcoming her and enjoy.
Thank you for the intro. Oh, can people hear me? Great, yeah, hi, nice to meet you. I'm Sewon. I'm a faculty member at UC Berkeley working on natural language processing and also researcher at AI2. I'm really excited to give this lecture about large language models today. I'm sure you have heard about exciting topics on generative AI earlier today and also yesterday, focusing on visual data and diffusion models. But today I'll give you a lecture that switches gear and talk about a different modality, which is natural language. And the generative AI models for this is large language models. I'm biased because this is my research area, but I also think it's one of the most exciting areas in generative AI. Arguably, large language models started the breakthrough in generative AI and is still continuing to make some of the most significant breakthroughs in the field. So yeah, I'm very excited to give this lecture. So the content of this lecture will be as follows. First, I will give you a brief language model 101, since this lecture is probably the first lecture that is formally covering large language model. And I'll deep dive into the architecture of large language models, that is architecture called transformers. So we'll deep dive into that. And then lastly, I will briefly talk about how we can augment large language models to be more factual and grounded by using a technique called retrieval. It's called retrieval-based large language models. So that will be the top content. And I'll get started with language model 101. I'm sure all of you have heard of the word language model, but what's the definition of a language model? In media, people often think of it as products like ChatGPT, Copilot, Gemini, Cloud, or DeepSeek. But this is actually not the original definition of language model. So what's a real definition of language model? So language model is a model that assigns a probability score to every possible text sequence in the word. So it assigns a probability score for how likely this sentence is. It can do that for any kind of sentence. So for instance, it should assign a pretty high score to the sentence like Jane went to the store because it's a pretty likely sentence. It's a pretty probable sentence. But it would not give a high score to a sentence like store to Jane went though, because this is not really a sensible sentence. It should also know that a sentence like the capital city of California, Sacramento should get a high score because it's a very likely sentence and it's also factual. It should give a lower score to the sentence, the capital city of California is Berkeley, because this is not factually correct, but it's likely still give a reasonably high score for the sentence because it still makes sense. And then for a sentence like the capital city of California is store, it will probably give a much lower score than the other two because store can't really be the capital city. Here's a quick quiz. So there is a model called GPT-2 Small. GPT-2 is a previous version of GPT-3 and ChatGPT from OpenAI that came up in 2019. And small means it's a small variant of GPT-2. It has about 100 million parameters. That's about 2% of the total parameters modern large language models we have today have. So it's a pretty tiny model. What would this language model assign a score to each of this sentence? So let's look at the first sentence. So it assigned 1.5 times 10 to the minus 8 to the first sentence. So even though this is a probable sentence, the value is very small. And this is because there's so many possible text sequences out there, so your denominator is really big. So that's why the score is low, but it's still much higher than the second sentence, which is getting much tiny score because this sentence does not make any sense. What about the other 5 sentences? I'll just give the answers. So it assigned a score. So for the first 4 sentences, it's giving a reasonably high scores because these are all sensible sentences. And then for the last one, because it doesn't make sense that store is a capital city, it's assigning a much lower score. So you can see that the scale of these values kind of makes sense. But did anyone notice something weird here? Mm? Oh, second. Yeah, yes, correct. Yeah, so it's giving a higher probability to Seattle, which is not factually correct. It should give a higher score to the first one, which is Sacramento. So if the language model is really good, it shouldn't happen. It should be able to assign a higher score to the first sentence because it's more probable. But because GPT-2 small is probably a small model, which means it's maybe not as capable as the larger ones, it's making a mistake like this. I also show some scores for GPT-2 large. It's also the same model family, also GPT-2, which is a previous variant of ChatGPT, but now it has way more parameters. It's about 5 times more than the small variant. And now we can see the values look like this. It's pretty similar. The first 4 sentences have a pretty reasonable scores. The last one have a much lower score. But here we can see that the first sentence, which is a correct sentence, is getting a higher score. So now the model is larger, so it's more capable. It's able to know that the first sentence should be more probable than the other sentences. Okay, so far I mentioned that a language model's original definition is that it's assigned a probability score for the entire text sequence. But another definition that we can take is that given a text prefix, it assigns a probability distribution over what word should come next. We call it token, so we use a token here. We'll talk about it later, but for now, you can think of token as the same as the word. So a language model defines the probability distribution over all possible words given an arbitrary text prefix. And you can see that this is almost equivalent definition of the previous definition because once we have this model that can assign a conditional probability over a text prefix, it is trivial to assign a probability score for the entire text sequence. So for a score like P of the capital city of California, Sacramento, it's basically P of the multiplied by P capital given the and until the end. So for now, we will take this new definition, which assign a probability score for the next token given a text prefix. So if you have, this is another illustration of a language model. So the input, which is a prefix of a sentence, is the capital city of California, and it's basically outputting the probability distribution over all tokens. Here we show some multi-words just to make it easier for visualization, but this is how the output typically works. And you can see if the model can output a probability distribution over words, it can also predict the next word because it can just take a word that is giving the maximum value. So a language model can also be seen as basically the next token prediction model. So what can we do when we have a model like this? So first we can do things that we already discussed, like scoring sequences. For instance, knowing that the first sentence should be more likely than the second sentence. It can also complete a sentence. So given a prefix like the capital city of California is, it should be able to predict the next word because it can basically take the argmax. And here it's one word, but you can think it can also complete a sentence with multiple words. So it can also generate long form text generation. And that's because if you iteratively do next token prediction, it can basically complete the sentence with a long text. And what that means is you can also do a bunch of different things by putting the input appropriately. So for instance, if you want to do question answering, meaning you have a question that you want to get an answer, you can form the input like this, which is Q column, what's the capital city of California, and then A column, so that it is very natural that the completion of this input would be the answer to the question. So if you give an input like this to the language model, it should be able to complete a sentence that is basically the answer to the question. You can do all sort of different things, not just question answering. For instance, if you want to do translation, then you can give an English sentence and then put an indicator like Korean column, and then it will give you an output that is a Korean translation of the given English sentence. You can do many different things like story writing. You can ask the model to write a short story about a girl living in California, and this is the actual text that the language model generates. It's able to generate a long form text like this. You can also ask the model to do something more complicated, like generating instructions to go to a place from another place, and it's able to generate a pretty long and also well-formatted text like this, which also have bullet points. So yeah, so in summary, original definition of language model is really just a next token prediction model. So given a text prefix, it's able to predict the next word. And if you do it iteratively, then it can basically complete and continue any given piece of text. And what that means is that many different downstream tasks we care about that involve natural language can in fact be casted into a text completion problem. So if you can format the input in the right way, you can give it to the model, let the model to complete the sentence, and it will naturally perform a task for you and then give you the output you want. So that's how we can use this next token prediction model for performing many different downstream tasks we care about. Cool. By the way, feel free to interrupt me for any questions. So far we talk about a language model, but what is a large language model that we are calling today? So language model has some taxonomy. It can include many different things, and among language models, there are neural language models. That is a neural net-based language model, and among neural language model, there is transformer-based language model. That means you're using a neural architecture called transformers, which we will look into very soon. And among transformers, depending on the size of the model, some of them can be considered small language model, and some of them may be considered large language models. And of course, the boundary is not very clear, but this is roughly how we define. What are the examples of language models that are not neural models? There are models like n-gram language model. For models that are neural but not transformers, there are models like LSTM-based language model. And for models that are transformers-based but not large, include examples like GPT-2, which are some of the small models we saw earlier on. So there are many different taxonomy that we can put here. We'll not go into too much detail on individual of them, except for transformer-based language model. So I mentioned that large means they're large in size, but what does it exactly mean? So the concept of large language models was probably first established when GPT-3 from OpenAI came out in 2020. And what they showed is a graph like this, where x-axis is the size of the model. Typically, that means the number of parameters. And you can see it ranged from 0.1 billion to hundreds of billions. And then y-axis is accuracy. You can see there are three lines. We don't have to care too much about that. That just means a different way of formatting the input. But the important part here is you can see as you grow the size of the model, the accuracy goes up. So if you increase the number of parameters of the model, that means the model is larger, and typically the model performance goes up consistently. But it also turns out that it's not just about the number of parameters, it's also the size of the training data. For instance, these are the graphs from scaling law, which is one of the very important concepts in establishing large language models. If you look at the graph on the right, that's the graph similar to the one we saw earlier. So x-axis is the number of parameters. Y-axis is something called test loss. You can think of it as sort of an accuracy, but the lower the better. So we can see as you grow the number of parameters, it decreases test loss, meaning it's improving the accuracy. But then in the middle graph, there is another orthogonal graph where the x-axis is now the size of the training data. And again, as you grow the training data, the performance goes consistently down, consistently up. And then if we aggregate these two graphs, then now we have the graph on the left, which means the compute used for training. And typically the compute for training can be seen as the size of the training data multiplied by the number of parameters. And if you look at this graph, then again, as we grow the compute, the task loss goes down consistently, meaning the accuracy goes up consistently. So in summary, when we say a language model is large in size, it really means it's large in terms of the number of parameters and the training data, and both are equally important. So how large is today's language model then? So I'll use an example from Llama 3.3 70 billion. This is a model from Meta that was released the end of last year, and it was downloaded about millions of times for the half year. So it's a pretty popular choice of large language models. The name is quite long, but basically here the llama means the name of the model family. So you can think of it as like a brand name. 3.3 means it's a version. So we had llama 1, 2, 3, and now we have 3.3. Now we have 4 more recently. And then 70 billion means the number of parameters. So it has 70 billion parameters. And then instruct means a variant of training method that we'll see later on. So as you can see from this name, it has 70 billion parameters. And in raw size, it is 140 gigabyte with half precision. And then in Llama paper, they reported that the training data size is 15 trillion tokens. And in raw data size, it's about 100 terabytes. So it's pretty big. And today we have models with fewer parameters, more parameters. Some of them are smaller or larger, but we can think of this model as one of the examples of the scale of today's large language models. And speaking of Llama 3.3, you can also try it out because the weights are public. So for instance, you can visit the website here in Hugging Face and you can try out the model. So for instance, I actually tried the story generation input that I showed earlier, and it's able to generate really long text like this. And if you look at the story, it kind of makes sense. It's relevant to the input. It's very fluent. So far I talk about the concept of large language models, but not much about training. I think we'll cover that in the next lecture in the afternoon. But just to summarize, how did large language models become so good so they can perform so many tasks that even humans find difficult? So there are 3 basic ingredients that led to the success of large language model: data, architecture, and compute. So the way large language model works is you first collect a large amount of web data, typically trillions of tokens, like in the Llama case, and you have a neural net that has many parameters, like tens of billions of parameters, and then you train this neural net on this large amount of data. And the way it works is that given any prefix of this data, we feed into the model and then let the model to generate the probability distribution over the next token. And then since we also know the ground truth next token of this sequence, we can maximize the likelihood of the correct token. And the key part here is that you don't need any human labeling for that, because you can have this objective from raw text data without any explicit human labeling. So you do that for billions and trillions of tokens. And once training is done, this model is able to remember many information from the training data and perform the task. For instance, if you ask a question like the capital city of California, it can remember that some training data mentions that the capital city of California is Sacramento, and is able to predict that word. And this is a very basic idea. If we look at the training objective, there's nothing special, but it really works well in practice, especially when there is sufficient scale. Again, meaning there is enough training data and enough number of parameters. And it's amazing that the model learns so much from the web data. And it's really possible because web data is so large and diverse. It makes the model to learn many things about the language, word knowledge, and also the format. So for instance, it will see a lot of text from formal language to informal text. And you will see a lot of word knowledge from texts like Wikipedia and even research papers. And it sees a lot of format that humans are familiar with, like question answering or conversation. So because this model has seen so much data like that, at test time it is able to know a lot of aspect of language. It knows a lot of word knowledge so they can answer questions about it. And it also knows the kind of format it should be familiar with, like answering a question or a conversation. Oh, so that was about the data, and I think Kyle will give another lecture in the afternoon to deep dive into the data. But data is not enough. You also need a lot of compute to make training possible. So one of the reasons large language models were so successful is because we managed to have computational power that can train very large neural network on a lot of text data. And then the second part, the last part that is also important is the neural net architecture, because it's not like a random neural network can train on that. The architecture has to be designed and engineered in a way that it scales very well with respect to the network size and the training data. And basically, modern large language models have transformers as the architecture. So we'll deep dive into that. You can think of transformers as a outcome of many years architecture search. So yeah, that's it for language model 101. And now we'll move on to the architecture about transformers. Any question? Yeah, that's a great question. And yeah, we have a brief content talking about that, but I can give you a short answer. So actually during language model training, there's nothing special the model does to handle these questions, handle this concern. So it's just seeing lots of data, and the whole assumption here is that if some sentences are factual, there are more seen during training so that the model naturally knows that this should be more probable than the other. Now in practice, well, it works quite well in some cases, surprisingly many cases. Like it is true that this makes the model more factual, but it also makes a lot of errors, like you mentioned. So there are many techniques to deal with that. For instance, there's some techniques called post-training, where after the model is trained with a language model and objective, you train the model in a different way so that it would be more factual. You can also use retrieval, which we will cover in the later part of the lecture. Yeah. Okay. Any other questions? Yes. Yeah, yes, great question. So in the lecture, I kind of kept it simple and said it will take a argmax, but in practice, you're right that often it does sampling. So the problem of only taking the argmax is that it can go to the local minimum very quickly, because oftentimes your goal is not to just generate one word, but generate a long sequence. You have to do it repetitively. And what could happen is that for every step, you're making a local best decision, but then globally, it may not be the best decision, and sometimes it can lead to some problematic sequences like repetition. So in practice, what people do is to do some sort of sampling that, and also some like ranking after sampling, so that it makes sure that globally it's a sentence that makes sense. Cool. Yeah. Now I'll move on to transformers. So in this part, I'll mainly talk about the original transformers, which is first introduced by a paper called Attention is All You Need. This is a paper in 2017. And maybe you've noticed, but this is a year where we didn't really talk much about large language models. And the original paper was not even about large language model. It's about machine translation. So this is a model that is specifically trained for machine translation and can only do machine translation. And only later, yes, it shows strong result on machine translation. And it's only after a few years that key papers like GPT-2 and GPT-3 picked up transformers and showed that this is an incredibly powerful architecture for large language models. And that was when people sort of realized that transformers can be really powerful architecture for training a large language model that doesn't just do one task like machine translation, but can do many different tasks like we discussed earlier on. And basically, transformers can be seen as a sequence-to-sequence model that is based on attention. It's one of the key operation of transformers that we will see very soon. Because the original transformer is not really about language model, but it's for machine translation, the architecture looked like this, and we often call it encoder-decoder. Encoder is responsible for reading the input, which is a text in one language, and decoder is responsible for generating the sequence. But nowadays, we are using transformers for large language model, which is mainly a generative model. So these days, all the architecture we are talking about will be decoder-only models. So in this lecture, I'll also assume that the transformers we're talking about is a decoder-only model. This is a brief overview of transformers, and I'll go it one by one. So first of all, there is some input layer that is taking the input text, tokenize it to a list of tokens and get the vector representation for every token. We'll call it input and embedding, and we'll talk about what exactly it does. And then it has a stacked layers of transformers. So it's basically L layers of a transformer layer, which is a basic building block of this whole large language model. And we'll talk about it very soon, but basically what each transformer layer does, it takes vector representation for every token from the previous layer and update it so that it considers the surrounding context in the given sequence, and then give the updated vector representation to the next layer. So it does this process L times, and that's basically stacked transformer layers. And then after the final layer of transformer layer, what we do is basically just take the vector representation for the last token, which is vector over there, and then fit into the layer called a softmax layer. And what it does is, given a vector representation, it transforms it to the probability distribution over all possible next tokens that look like this. So that's the basic overview of transformers. So I'll go in one by one, starting from the input layer. So the very first thing this model does is, given a text prefix, it split it to a set of words, more precisely subwords called tokens. So for instance, given a sentence like the books were improved, it can be split it into this. So it's sort of like words, but you can see that some words are split it into more fine-grained level. For instance, books were split it into book and s, and improved is split it into improve and ed. So there is a thing called tokenizer, which is a function that can be applied to any text to make it a list of tokens. It's typically predefined even before we start doing any training. So once we have a list of tokens, now we should have a vector representation for every token. We often call it input embeddings or just embeddings. And basically how that works is, there is a lookup table. It's basically a matrix of size v times h, where v is a vocab size, that means the number of unique tokens, and h is a hidden dimension, which is a hyperparameter for the transformer model. So every unique token has some vector representation that is assigned to it. And then once we transform the input sequence into a list of tokens, we can just map it and put the corresponding vector representation as embedding. So that's pretty straightforward. But another weird thing transformer does is to add a thing called positional encoding. And what that does is as follows. So word embedding can consider what the word is, but it doesn't really consider the position of each token. For instance, given these two sentences, the dog chased the cat and the cat chased the dog, and of course these are two totally different meanings, but then if you just use the input embedding, the dog in the first and the second sentence will have the same vector representation. And same for the cat. The cat in the first sentence and the second sentence will have the same representation, which may not be exactly what we want because they mean different things when they are placed in the different location. So what people do is to add a positional encoding and add it up to the embedding so that now the vector representation of the word considers the position. And there are many different ways of defining or getting the positional encodings, but what original transformer paper did is to use an encoding called sinusoidal encoding. Basically looks like this, which is considering some sine functions and cosine functions as a function of the position, which is t here. If you feel this function is sort of random, I think it's very natural. It looked very random to me. So these are basically engineered empirically. But later, people also find a better positional encoding, which we will briefly discuss later on. So once you have embedding and positional encoding, you now have a vector representation for every token. And now we'll move on to a stacked transformer layer. This is a outline of the transformer layer from the original transformer paper, and where the thing in the box is one transformer layer. You can see it basically repeats 4 operations: multi-add attention, add a norm, feed forward, and add a norm. So we'll look into that one by one. So the first operation is multi-add attention, and to understand this, we should know what attention is. And to put it simply, we can think of attention as a thing where each element in a sequence attends to elements of other elements in the same sequence. There are 3 key concepts: query, key, and value. And you can think of this as this way. Query is a thing that show the model, here's what I'm interested in. Key is the thing that tells you here's what I have. And value is if you find it interesting, this is what I will give it to you. So it determines the output. More formally, what happens is as follows. So these are query, key, and value are all matrix of size L times H, where L is the length of the sequence, so it's a number of tokens in your input sequence, and H is a hidden dimension. And then you multiply Q and K, which means for every query key pair, you will calculate some sort of weight based on a dot product. So it indicates the similarity between query and a key. So if they are more similar, you'll get a higher score. If they're less similar, you will get a lower score. And we use it to compute the weight. So once you compute this dot product, you normalize it so that it will be a value between 0 and 1, and it's summed to 1. So it can be a proper weight, and then now you can do a weighted average using V, the value. So you can think of it as a weighted average where weights are computed based on the similarity score between a query and key. One small problem here is that the scale of the dot product can increase as the dimensions of the vector gets larger because it's basically summing up over all element-wise multiplication. So what transformer does is to normalize it by square h, where h is a hidden dimension. So we call it scaled dot product attention. So that is an attention, but what is self-attention? That means we are doing attention over yourself. And more precisely, each token in a sequence is attending to all the other tokens in a sequence. Formally, what that means is that there is a representation that is coming from the previous layers of transformer. We'll call it H, and then we'll repeat this H to use it for query, key, and value. So you apply attention function to H, and then you get some output, which is the weighted average we discussed. Then it will be the input to the next layer of transformer. Cool, yeah. So that was the self-attention, but what is multi-head attention? This is actually the easiest part. It just means that you'll do self-attention multiple times. The intuition here is that there can be multiple different ways of attend to the other tokens in a sequence. And if you can model all the possible ways of attending to the other tokens in a sequence, you can get benefit. Practically, what it means is as follows. You still have one matrix from the previous layer. We repeat this so that we have query key and value. We multiply by weight so that they will have slightly different values. So the matrix look like that. And then what you do is to split it and arrange it so that it will be n different inputs with the same dimension. So in this graph, in this plot, n is 2 because you want to do 2 self-attention. And then once you have the small matrices, you can apply self-attention to every individual one independently. So you'll get the attention output for each of them. And then finally, you can concatenate it so that it can eventually become a single matrix. And the single matrix can now be the output of the final multi-head attention and can be fed into the next layers of transformer. Any questions here? Yeah, so that was multi-head attention. So going back to the plot from the transformer layer, we talk about multi-head attention. The next is add and norm. So add means residual connections. And basically what it means is instead of using the output from the attention layer directly, it will actually add up with the original input that was before attention. And so this concept of residual is actually pretty popular and it has existed before large language model, originally developed for convolutional neural network. And the intuition here is that when the neural network is very deep, meaning it has many layers of some blocks, then it's very easy to have a vanishing gradient problem, which makes training very unstable. But if you have residual connection like this, then it can prevent vanishing gradient and make training more stable. So that explains the add part. And then the norm is basically a normalization of the input you have from the previous layer. So this means for every layer, because the parameter values are very different, the output from each layer can have very different scale. So you want to normalize it so that they will have a pretty consistent scales. There are many different ways of normalizing. The original transformer used a thing called layer norm that normalizes the values across the mean and variance. And there are many variants of that we'll briefly talk later on. So that explains add and norm, and then the remaining part is fit for layers, and this is a pretty straightforward. It's same as fit for layer in any machine learning models. It's a linear model that is adding a non-linearity like a ReLU function, and it's useful for transforming the feature vectors. Okay, so that was about transformer layers, and we have stacked of them. And then, as I mentioned earlier, in the final layer transformer, we have vector representation for every token. And then finally, we'll only take the one from the last token and then give it to the softmax layer to get the probability distribution. This part is pretty straightforward. So given a vector representation from the last layer of transformer, we use a matrix that is a size of V times H, where V is the vocab size. That's the number of distinct tokens that we saw earlier in the embedding layer. And we multiply by that, and we'll have a vector that is V dimensional. So now we have a real value for every possible token. Now we want to transform it to the valid probability distribution. So that's where we apply softmax function. And it's simply a way to transform the real value to a value between 0 and 1, and then the summation to be 1. So if we go through the softmax function, then it will give you a valid probability distribution over all possible next token. So that's it. Is it clear? So I'll just do a recap in code. So this is a transformer block, meaning one layer of transformer. We'll mainly look at the for function. So given a matrix, which is the output from the previous layer, it does pre-normalization, like layer norm, and then it goes through self-attention, and then it'll go through added norm, which is residual connection, and then another normalization, and then it goes through a feedforward network, and then another residual connection, and that's basically the output from the block. You may notice that there is one discrepancy between the previous content and this code, which is now the normalization is at the beginning of the transformer block, not in the middle. We'll talk about what that is later on, but this is a implementation of the modern transformer model. So this is one layer transformer. Now for the actual transformer language model, it looks like this. So in the beginning, we have X, which is a model that is, which is the input that is already tokenized, and then it goes through the embedding. So this is the embedding model. And then we add a positional encoding, which is this. So the summation of them will be final vector representation for every token in a sequence. And then now we go over all the transformer blocks. And naturally, the output from the previous layer will be the input to the next layer. And then once it is done, it will go through the final layer. And as you can see, there is another linear operation where it's multiplying with a matrix of hidden dimensions multiplied by vocab size. That's logit, meaning that every possible next token have a real value. And then outside of this function, it will go through the softmax so that it can transform it to the valid probability distribution over all tokens. Any questions so far? Yes. But vocab size and the number of parameters is different. Vocab size means the number of unique tokens, so number of unique words, for instance, and typically that's a scale of 10K to 50K. Parameters means the number of learnable real values. So for instance, the embeddings, because it involves a matrix, that's part of the parameter. All the matrices that we use for transformers blocks and also for the output layer, these are all learnable parameters, and that's count as parameters. Yes. I see. So your question is when it's just given a vector representation like X, how does it know it's from the embedding and it's from the positional encoding? Yeah, it doesn't really know that. And I think the idea is it doesn't have to know that. Like it's just a summation of two matrix and the model can just learn how to distinguish them. Yeah, and at least in the original transformer, the positional encoding is actually deterministic, so there's no learnable parameters. So you can think of as just a bias term. And then the actual learnable thing is the embedding matrix. Mm-hmm. Okay, this one? Yes, yes. So that's the residual connection, meaning that you're summing up the input before the attention layer and after the attention layer. Oh, good question. Well, you know what? Like, I think there's so many questions about this architecture, not just why, like, we have two regional connection. Like, why do we have attention and then add norm and then fit for each a very particular design? Why should we do that? I think there could be so many questions that I don't have answer, but I think it's easier if you think of it as just like an outcome of many year architecture search. Like people engineered it and then found that it works empirically and it scales, and that's how people design architectures. Yeah. Yep. Yeah, great question. So later on, like people made a variant of the original transformer, like uh, grouped query attention that makes some modification to make it more efficient. But it's still true that computation is like scales with n square, where n is the length of the sequence. So maybe the simple answer is people haven't exactly figured out. It's actually interesting because how to efficiently model a very long sequence is actually one of the hottest research topics in LLMs, and there has been many papers that try to make it more efficient. For instance, doing some sort of attention approximation or doing some modification to make it linear. But to be frank, I think none of them actually really like turn out and be implemented in the frontier models that we'll see. So still the state-of-the-art models we're seeing is still doing quadratic attention that scales with the length of the input. Yeah. Yeah, that's a very excellent question. So that's very interesting because actually historically the very first um arguably the first transformer based language model is actually encoder based. That means it's not actually autoregressive. It's given a sequence with a blank and then it can fill in the blank. That's not really generative. But then the field continuously move toward more like a generative case. So people move from encoder to encoder decoder, and now people move on to decoder. So first is I think the benefit of either encoder decoder or decoder over encoder is pretty clear because encoder cannot really do text completion, which is one of the key part of like scaling this large language model training. Between encoder decoder and decoder, it's actually little unclear. Like people have worked on encoder decoder, but companies that train a very large language model somehow investigated more on decoder only, generative only model. I think there could be two explanations. First is decoder only model is easier to scale because if you just give the entire text sequence to the model and then train with the next token prediction objective, it can actually automatically get signal for every individual token. So you're just doing one feed for path, forward pass, and then you're getting signal to every token. Whereas in encoder decoder, you have to decide which goes to the input, meaning it goes to the encoder, and which part goes to the decoder. So it's more the decoder only model is more sample efficient. The second reason that I think is like not an official reason, but I think it's pretty convincing, is that encoder decoder has way more hyperparameter than the decoder only model. So when you scale the model, you have to be very careful on fitting the scaling law, decide which hyperparameter makes sense, and it's just much easier to design such a thing with decoder only model because there are just fewer parameters. So as far as I know, I think still one of the large encoder decoder model is like about like 11 billion parameters, whereas decoder only model we have like over trillions parameters. Oh, yeah. Yes, yes. I think you're exactly right. It's unclear. And I think even for LLM experts, I don't think it's pretty clear. And actually, I just talk about the architecture of the original transformers. And nowadays, people are actually making some slight modification to these architectures. And even if you look at the architecture from different companies, their architectures are not identical. They are all pretty different. Some of them, they converge on. So we know that oh, this is a little more they have a bit more consensus, but many of them, there is no consensus. So I think it's like pretty natural that not every design choice is super intuitive, and it's really the outcome of many efforts of architecture research. I think we can still try to make sense individually. Like for instance, people make sense of this residual connection because this is a way to prevent vanishing gradient, and people kind of make sense of normalization because this is a way to make scale more consistent. So I think element-wise, it's possible to make sense of it, but there's so much search space, and eventually how to make the final architecture is really the outcome of a lot of engineering effort. I can finish the transformer section and then take more questions. So cool, yeah, so far I've talked about the implementation of the original transformers, but as I briefly mentioned just now, nowadays people are making slight modification to improve the original transformers, and they made modification in many different ways. So one of thing is to make positional encodings better. So for instance, I mentioned previously the positional encoding is not learned, it's deterministic, but you can add parameters to that so that it should be learnable. You can also use something called rotary positional encodings, which is apparently very effective for long context extension. People also change the ordering of blocks. For instance, putting the layer norm not in the middle of the layer, but to the in front of the block. And actually, this is one single thing that we now have a consistent consensus on. So all the modern large language models are all using this thing, which is called prenorm. And that's why the previous code implementation is also using prenorm. People also make a modification of normalization by replacing layer norm to some other variant like RMS norm. And we'll talk about it a bit later on, but it's basically a simplified version of layer norm. And people also do something like group query attention, which is to make the attention more compute efficient. I don't think we need to go over individual of them one by one, but I'll just talk about two things. One is pre-norm versus post-norm, because as I mentioned, this is a pretty established right now, and nowadays all the modern architectures are choosing pre-norm. And the basic idea is just to move the position of the norm to be right before multi-head attention. So the relative ordering is actually the same, but where exactly it's putting is different. This idea first came from the 2020 paper, which stated that the benefit of this is to remove warm-up. But nowadays, I think for practitioners, prenorm is found to be useful to make training more stable and be able to use higher learning rate, which apparently makes large language model training more efficient. Another thing that is probably second most thing that has a good consensus is layer norm versus RMS norm. So as we saw earlier, the layer norm does normalization based on the mean and variant, and there are two parameters, the weight and the bias. And this is pretty good, but the point of RSM norm is we can make it simplified by removing all the parameters and then not computing mean. And it's just faster because it's fewer operation. Now you don't have to compute the mean, and it's also fewer parameters because now you don't have any weight or bias. And so it's faster, but it's also as good as layer norm. So now most of the modern architectures are using RMS norm instead of layer norm. But other than these two, as I mentioned earlier, different model architectures are making slightly different choices on how exactly they implement transformers. I just have a brief table that compares the original transformers, Llama, which is Llama 1, and Llama 2. So you can see that for norm position, they converge to prenorm. For norm type, they've converged to RMS norm. For non-linearity, that goes to the fit-for network. Instead of ReLU, they're using a thing called SWI-glue. For positional encoding, they're using ROP, which is the rotary-based positional encoding. And then for attention, Llama 1 was still using multi-head attention, and Llama 2 is using group query attention. One question you may have is, these look pretty minor changes. So how much does it actually matter in terms of performance? So I'll just show one graph from another paper that is not the llama paper or the transformer paper. It's a paper from Gu and Tao. They compare many different models. Y-axis is perplexity. It's kind of like accuracy, but then the lower means better accuracy. Here they compare many different models, but we can think of transformer as the original transformer and transformer plus plus as the implementation of llama 2. And if you look at the graph, you can see transformer plus plus is able to get the same performance as transformer with 10x more flops, meaning 10x more training compute. So that means if you're able to do better architecture search and engineer the architecture well, then you're able to make the language model training up to 10 times more efficient. And I'm pretty sure that this is still on, there's still a lot of ongoing effort how to make architecture even more efficient and more engineered. Yeah, this is the end of the section about transformers. Any other questions? Cool. So now I'll move on to the next section, which is retrieval-based language models. So for this part, we will come back, assuming that transformer is just a black box that is given to us, and talk about how we can interact with these large language models. So as we discussed in the beginning of the lecture, the way language models is trained today is as follows. We first collect a large amount of data from the web, like trillions of tokens. We have a large neural net that has tens of billions of parameters, and we train this model using a next token prediction objective, which is given a prefix and is trained to maximize the likelihood of the correct token. And once training is done, the training data be disappeared, and we are only relying on these learned parameters to make an inference. And because these parameters can remember many information from the training data, it's able to answer a question about word knowledge, like the capital city of California is Sacramento. So this is surprisingly effective in practice, especially with large amount of data and a large amount of trainable parameters, but it's also very expensive to train. And the problem is that we are making an assumption that training this neural net on a large amount of data is able to make the model remember every detail from the training data, which is not really true. It can remember facts if they're being repeated over and over on the web, but if something is rare and it's not repeated over and over on the web, it's not able to remember that. Another problem is that it's not able to keep updated. I just put an example about my biology biography, and then it's without web browsing, it's not able to make a correct answer. It's making some factual errors, and it's also not updated. So basically, large language models still have many problems, and among them, the three key limitations is that they're very expensive to train, they still fail to remember details, especially for long tail facts, and it fails to stay up to date unless you retrain the model. So the idea of retrieval-based large language models is instead of discarding the data after training, you keep the data and use it at test time. So for instance, given a test input like this, it's able to locate relevant piece of information from the data and reason over them to make a prediction like this. And this location function is, so that it doesn't need to remember everything in the training data because now it can look it up. And this location function is called retrieval. You can think of it as an information retrieval like Google search does. And this data that you keep at inference time is called a data store to distinguish it from the training data. Now, the key idea here is that this data store doesn't even have to be static. It can be updated after training is done. So you can grow the data if you manage to have more data after training. And you can also keep it up to date if you have up-to-date information you want to add. So for instance, we can add breaking news to the data store so that the model can retrieve relevant up-to-date information and be able to generate the response over them, even if that information was unseen when the model was trained. So that's a key idea of retrieval-based model, and I already briefly talked about the advantages, but just to summarize again, retrieval-based language models are simply more performant, especially when it comes to the long-tail knowledge, and it's also able to stay up to date. This is an updated ChatGPT response with, this is a previous ChatGPT response, and this is a new ChatGPT response when I'm enabling the web browsing function, which is basically like a retrieval. So it's able to retrieve relevant information about myself and be able to stay up to date. Here is another data point from one of our papers that showed the factual accuracy of ChatGPT and Perplexity AI. Perplexity AI, at least at the time of writing the paper, is basically the retrieval-based version of ChatGPT that is using retrieval and then ChatGPT. And x-axis indicate the frequency of entities, so frequent to more rare. Y-axis is factual accuracy. So there are two graphs, but you can just look at one of them. So we can see that for questions about frequent entities, both models are able to achieve a pretty good score. But as the entities become more rare, ChatGPT struggle a lot. And Perplexity also struggle, but they're much better than ChatGPT. So when it comes to long-tail entities like this, using retrieval is almost always helpful. So another reason for using retrieval-based language model is if you want attribution of your text generation back to the data. So for instance, this is an old interface of Bing Search, which is able to provide citations to every factual information that it is generating. So it's giving some numbers, and you can visit the original website to verify and fact check the information the model is generating. And this is good for explainability. It's good for high-stake applications where factual correctness is very important. And as you can see from today's ChatGPT, Gemini, and all the other models, frontier models are already using retrieval as one of the key features, especially by combining a commercial search engine together with the language models they already have. So that was about performance. The second reason that I think is as important for using retrieval is it's just more flexible to use the data. So for instance, if you have some proprietary data sets, private data sets, or copyrighted data sets that are not exactly included in the training data, but you may want to use it in some way, then instead of putting it into the training data, you can separate them, but then use it at inference time so that the model can retrieve it. And in that way, you can make use of your private data sets that are not included in the training data of the models. And also it's more flexible. As I mentioned, the data store can be updated at any time, so you can edit when you have a new information, and you can also remove it if you don't want to use it anymore. It's also flexible in terms of the location. For instance, if you're using ChatGPT, the model parameters is remote, but you can use your local data store, or you can do the other way around, meaning you can use the remote data store while having your model parameters local. It can also give a straightforward attribution and credit assignment. So if some data is available data that you want to get paid for, then retrieval-based model give a straightforward way to do that because it's very easy to trace which part of the data contributed to the model prediction. So one way I'd like to think about it is that retrieval can be seen as an alternative way of using the data, which is orthogonal to using data to training the model, and it has different trade-offs. So that's a brief benefits of retrieval-based model, but how do we actually implement that? Simply put, it's a two-stage pipeline that consists of two stages, retrieve, then generate. Given a text input like this and a data store, which is a large collection of text documents or text passages, we can use a retrieval system to retrieve a set of documents or a set of passages that are most relevant to the text input. And once you identify a small set of passages, you can fit into the language model together with a text input and let the model to make a prediction like regular language model does. So the first part is called retrieval and the second part is called generation. We can go over it one by one in more detail. Oh, and I also want to mention that this idea of retrieved and generated is actually the older idea that existed even before large language model or even before neural language model. But this idea has been sort of reframed so that it can be useful for large language models. So I'll get started with the first stage, which is retrieval. So formally, a retrieval problem can be written as this. So in the data store, we had a set of passages, C1 to Cn. And at test time, we have an input X. And our goal is to identify Y, I, which is one of the passages in the data store that is most relevant to the input X. We can easily generalize to retrieve K passages instead of one passage, but this is pretty straightforward. So we'll just assume we are only interested in one passage. And usually K is pretty small, about 100, where the total number of passages in a data store can be millions or billions. So this is a pretty tiny fraction of the entire data store. There are many different ways of doing this retrieval operation, including some rule-based systems or non-neural model. But in this lecture, I'll talk about the neural approach to solve this problem, which is also known as a Siamese network. The basic idea is this. So we have a neural encoder, which map every text into a vector representation. So we can think of it as having some shared vector space like this, where encoder maps every passage into one of the dot, which is one vector representation in this space. And this encoder can do this for every passage in a data store. And typically this can be done offline before the model is being deployed. And then when you have a new test input, you use the same encoder to map it to the same vector space, and then identify the closest vector and return the corresponding passage as an output. Actually, doing fast nearest neighbor search, meaning identifying the closest vector over millions or billions of candidate vector, is not an easy problem. But fortunately, there has been research done here for decades in database and algorithms. So now we are able to do pretty fast nearest neighbor search over billions or billions of vectors. So typically, this is a sub-second latency. So far I talked about neural retrieval. Now I'll talk about generation, which is pretty straightforward. Let's say we have a set of retrieved passages like this. So we have 3 passages and we have a test input. Then what we can do is we simply take the first retrieval passage, which is probably the most relevant one, concatenate it so that it becomes a single piece of text, fit into the language model, and let the model to make a prediction. So it will output a probability distribution like this, and we can take an argmax to make a prediction. It's very, very simple. You don't even need to change anything about the language model internal. You can use a black box API-based model like ChatGPT. So it's very simple. And this works surprisingly well, especially if the retrieval result is good. So for instance, if the top ranked passage is indeed the right passage that is relevant to the test input, this works very well. The problem though is the retrieval is often very challenging and it's often making errors. So for instance, it often is the case where the top result is not the right passage, although the second or the third one can be the right passages. And in this way, if you're only using the top passage, meaning it's an irrelevant passage, then the model is not able to make use of it. In fact, it's even worse. It's even worse than not using retrieval because this passage can be distracting. So now the key question is, how can we make use of multiple passages? Because if we were able to use the second or the third one, which are potentially correct, then we'll not have this problem. There are 2 different ways of making use of multiple passages. One is concatenation. It's very straightforward. We have 3 passages. We concatenate into a single piece of text together with a test input, and then consider it as a single input that we can fit into the language model. And again, the language model can take this input and makes a probability distribution as an output. So again, it's very simple. You can use any black box API. The problem though is that it's strictly bounded by the maximum sequence length of transformers because the language model, especially the transformer architecture, usually have a strict upper bound on how long the input can be. And it also makes the inference very long because as you make the input longer, the cost will be quadratically increasing. So an alternate way you can use is something called ensembling, and it looks like this. So for every passage, we concatenate with the input text and fit into the language model independently. So the language model will independently output a probability distribution like that, and then we can aggregate them to make it a single probability distribution. Formally, it's a weighted average where weights can be a score from retrieval, and then the thing that we're averaging is the LM probability scores. This is good because it's no longer bounded by the length limit. Now you can technically incorporate an infinite number of passages. However, you still have the problem that increase the inference cost because if you want to use n number of passages, you need to make 4 passes n times. So none of them are perfect, I would say, but fortunately, the language model is pretty powerful and efficient. So even today's retrieval-based language models are using either of them to make a prediction. Any questions so far? Yes. Yeah, great question. Let me answer the second question first, which is, yes, I think this is a great way to reduce the size of the model, especially because at this point, one of the motivation for making models larger is to make it more factual, but if you use retrieval, that might be a simpler way of making it factual. And there has been lots of research that show that if you use retrieval, a small model can be as good as the bigger model. Regarding your first question, whether we can use a smaller amount of data. I think yes, in the sense that maybe retrieval can be a way to bridge the gap, but also retrieval is pretty orthogonal. So if you can use retrieval over overtrained model and undertrained model, then overtrained model is still always better. So I would say this is like complementary and orthogonal. It can make weaker language model to be as good as bigger language model, but still, if you can use retrieval on top of bigger language model, that's always better. Okay. Mm. Yeah, that's a great question. So, okay, so normally the hope is that the encoder is able to generalize because this encoder it's different from language model because language model works by memorizing information from the data, and after that the data is not there. So it's very difficult to generalize to unseen fact, whereas the encoder is given the data and is mapping it to the vector representation. So when you're given a new data, this encoder should be able to generalize. I think that's hope. And in most cases, it is a case. However, if there is a very significant distribution shift, for instance, maybe the encoder is trained on Wikipedia, but now you want to apply it to a biomedical sequence, then the distribution shift is so big so that you might want to retrain the model. My understanding is that for temporal shift, like maybe if it's more about up-to-date information, then encoder is able to generalize very well. But if it's a completely different domain, like a biomedical case, then it's possible that encoder has to be retrained or you need like a domain-specific encoder. Yeah, great question. Just to make sure I understand. So your question is are there any like consensus? So when is the case using retrieval is better versus fine-tuning or further training a language model? Yes, a good question. Yeah, so I think there is no like really good consensus, but general consensus is that if something is about like factual information or fact that may be mentioned like one or two twice in the data, then using retrieval is good. So because retrieval is very good at pinpointing the exact information you have in the data. So in that case, I think using if a retrieval is good. But if it's something more about the new domain or new patterns across a larger chunk of data that is not really like there is like one information that you can pinpoint, in that case, I think using it for training is probably more effective. Cool. That's a great question. Yeah, so I didn't really talk about training this kind of model, but that's a really good question. So actually, I think majority of retrieval-based language model is not really training with retrieval in mind. So in majority of cases, language models are just trained to be standard language models, so it's not using data store. Retrieval model is also trained in their way, and they were just plugging them together at inference time. So you don't really need a data store during training. However, there also have been efforts to train retrieval-based language model. In that case, you need some sort of data store, and it can give you additional gains. Typically, that can be different from the data store you use at inference time, because again, the hope is the encoder model is able to generalize even if you have slightly different distribution at test time. Yeah. I'll get the last question. That's a great question. Actually, I had a last slide about that, but just to give um give a brief answer, I think uh let me actually think how to answer. I think in the production systems, what's probably happening is that there is some mechanism to decide whether this requires retrieval or not, and only when it requires retrieval, it prompts the retrieval model. Otherwise, it would simply skip retrieval. In practice, if the language model is really robust, it should be able to just always call retrieval and then always use that even if retrieval is incorrect, because language model should be robust and be able to ignore if something is not relevant. And because retrieval operation is actually cheap, it doesn't really incur much cost. But in practice, language models are not so robust, so that it can be easily distracted by irrelevant passages retrieved by incorrect retrieval result. So I think that's why people are more interested in adaptive retrieval. Yeah. I only have a couple of slides, so let me finish that and maybe get more questions at the end. So I talk about a basic retrieval-based model that is two-stage, retrieval and then generation. But then nowadays, people are designing a more complex pipelines to use retrieval and language model in a more complex way. I think now people often call it agent or RAG agent. These are two representative papers that are some of the early works on designing agent with retrieval. They're really complicated and often domain and problem specific, but some of the key functions that they all have in common are as follows. So as we got a question, the language model should be able to decide when to use retrieval or not. So use retrieval only when it's needed. It should also know generating a retrieval query. So in the naive retrieval-based model that we saw earlier, we're actually using the original input exactly as a query, but now a language model is able to rewrite it in a way that it is more sensible retrieval query. Once retrieval result is done, retrieval can be incorrect or the ranking may be not good. So a language model can do additional re-ranking or doing some sort of adapted adoption after retrieval is done. And then finally, it can do some sort of rewriting. So after retrieving passages, it can rewrite passages to make it more comprehensible to the language model or keep only relevant information. So there are many different ways to design this agentic pipeline that is still an active area of research in the field. That was all about retrieval-based language models. So that's it for today. Thanks for staying. I just have one quick slide on the summary. So I started with language model 101, where we define language model as a next token prediction model. And by definition, it can complete and continue any given piece of text because it can repeatedly make a next token prediction over and over. And that means it can perform many different tasks that involve natural language because a lot of tasks we care about, like answering a question, translating on text, or generating a story can be casted into a text completion problem. Then we went to deep dive into the architecture of transformers. It has input layer that has tokenization, embedding, and positional encoding. It has stacked transformer layers where the key operations are multi-attention and feed-forward network, and it also has some add and norm operations. And then finally, it ends with the softmax that transform the vector into the probability distribution. We also briefly talk about various improvement after original transformer, like pre-norm versus post-norm and RSM norm. And lastly, we briefly talk about how to augment large language model with an external data store to make it more factual grounded. It's able to make LLM up to date even without retraining, and it's able to make use of private data. We briefly talk about how to implement this, which is a two-stage pipeline retrieval and generation. And there are many different ways to design a complex pipelines on top of that. So yeah, that's a quick summary of the lecture. And yeah, thanks for listening. And I'll take more questions. Oh. Yeah, great question. So to answer your first question, which is just to repeat, if the model is repeatedly making a next token prediction to complete a long sequence, if the model is making a wrong decision in first step, then would the rest of the steps get impacted, or is there a way to recover that? Yeah, that's a great question. The basic form doesn't have a way to do that, but there are variants of generation method that can help recovering that. One of the such an algorithm is called beam search. And what it does is when you're making a next token prediction, it's not just keeping the top one, it's actually keeping like n number, let's say 4 numbers, and then it considers the possible completion after that for every candidate. So it keeps this as all the candidates, and then once it complete the text enough, then it ranks them again using some global information so that it knows that which one is probable. So there is a way to do that. In practice, this candidate set can go really quickly because if we just keep 4 per step, it can go really quickly. So it's still limited, but there is a way to do that. Actually, it's interesting because I think this beam search was more popular a few years ago when large language model was not good enough. But then nowadays, I think it's actually less popular, likely because it is able to make a local decision pretty well. And especially if you're doing sampling, not exactly taken argmax, it is able to generate a pretty natural text even without this beam search. It's a very great question. So first of all, let me clarify that when I said earlier that there is some implicit assumption that most of the data on the web is factual, or at least like if we do some sort of majority voting, it should be factual. I think it is true that it's like, I think nobody really like truly believe on this assumption, but then like people are making this assumption because there's no way to exactly filter the factual data. But it's definitely not true. Even before considering LM generated data, even if it's human generated, they can have a lot of misinformation. It can be highly biased, and it is indeed true that these problems still exist. And I don't think there is an easy way to fix that now. People do some sort of quality filtering over the pre-training data, but the quality filter doesn't explicitly model how factual it is, so it's still very limited. Actually, I think the practical solution that these large companies ended up adopting is they just do pre-training, not caring about anything. They just do pre-training, whatever. But then at the end of the pre-training, they create a small number of data that is they verify more heavily to be factual, and then do additional training on top of that, so that you know that at least the recent data that this model have trained on is factual, and hope that is able to lead to the model more factual. But how to make model more factual is like really long standing problem that I don't think we'll have a solution very soon. And you also made a great point that independent of all of this problem of web data in containing misinformation by human, now there's contents generated by an AI model that is very difficult to distinguish from the training data. If some AI generated data can be like nonsensible, then it's easy to filter out through quality filter. But then if they're non-distinguished from the human data, then it's very, very difficult to distinguish it. And I think it's likely to be a very huge problem more in the future. So just to understand if just to make sure if I understand your question, so you mean retrieval-based models may still not be factual because it may look into the wrong passages, or even when there is a right passage, it may fail to look into that. So your question is, how can we ensure it actually is grounded to the right passage? Yeah, that's a great question. I don't think there's like a special technique for that. I think the hope is if the language model is robust enough, it is able to attend to the right passage. But I think you're right that yeah, like it may not always be the truth. Yeah, I feel like my answer is really vague because I think it's partially because how big companies that are training frontier models are not all public. So there has been research done, and I can give answers based on research, like people train in this way or that way, but it's not really clear if that's exactly the same as how frontier models are being trained, because the exact training recipe is getting more secretive over and over. But I think to answer your question, I think basically the simple answer is if they just make sure language model is robust enough so that they hope it is the case, and then potentially they can do additional training together with retrieval so that they can make extra sure that they are attending to the right passage.
Thanks again.